This video covers the properties and preparations of alkenes. Alkenes are unsaturated molecules that contain one or more double bonds. The presence of the weak carbon-carbon pi bond makes it more reactive than alkanes. It also restricts rotation, inducing cis and trans geometry of the alkene. Depending on the position of the alkene, it can be called a terminal alkene, an internal alkene, a cyclic or endocyclic alkene, or an exocyclic alkene. For cyclic alkenes, if there are less than 8 atoms in the ring, it's always going to be a cis alkene. If there are 8 atoms or more in the ring, then it can be either a cis or a trans alkene. Alkenes have low melting points and boiling points, and this is because they experience only van der Waals force. They are soluble in organic solvents, and there are different properties for cis and trans stereoisomers. These two isomers are not mirror images of each other, nor are they superimposable, and they are considered diastereomers. If you consider that the alkene sp2 carbon is slightly more electronegative than the sp3 carbon, you can tell that there is a small dipole moment towards the sp2 carbons in both the cis and the trans. Due to the geometry of the trans, these two dipole moments cancel out, and they have no dipole moment or a very small net dipole. In a cis alkene, they add up and you have an overall small dipole, and they're more polar than the trans alkene, and so they have higher boiling points. Just a note, cis and trans is not always the same as E and Z. E and Z is the terminology that's used for IUPAC nomenclature of alkenes, and it follows the Kahn-Ingold-Prelog priority rules, which is the same rules that we use for naming R and S stereoisomers. Alkenes can be formed from the corresponding alkyl halides using a dehydrohalogenation. For example, in this case, we have bromopropane, and we can treat it with DBU, which is a non-nucleophilic base, in order to form propene. In the second example, we've got another good leaving group, a tosylate. We can use potassium terbutoxide, for instance, to get the alkene. In this case, you have the possibility of deprotonating either at this position or at this position. Using the Zaitsev rule, we know that we will favor the more substituted double bond, and so our product is going to be the more substituted alkene. Alkenes can also be prepared from the corresponding alcohols using either acid-catalyzed dehydration or under basic conditions using POCl3 and pyridine. If you're using acid, you want to use catalytic strong acid like sulfuric acid or tosylic acid or phosphoric acid, and you'll end up with the alkene. Under basic conditions, you can use POCl3 and pyridine, and you will also end up with the same alkene. You can also prepare alkenes from the corresponding alkynes, and usually alkynes are reduced with hydrogen gas. Hydrogen does not do anything without a catalyst, and so under normal conditions you will use hydrogen with palladium on carbon as a catalyst, and this undergoes reduction to the alkene and further reduction to the alkane. Since we don't want this over-reduction to the alkane, and we would like to stop at the alkene product, we use a particular catalyst called Lindlar's catalyst. Lindlar's catalyst is considered a poisoned palladium catalyst, which just means that it is less reactive than just palladium on carbon. This usually consists of palladium on calcium carbonate or barium sulfate with lead tetraacetate or some other lead salts, and sometimes also with quinoline as a base. When you use Lindlar's catalyst, the alkyne is going to stop at the alkene. Just remember that you will have syn addition of hydrogen gas, and you will always end up with the cis alkene.